Welcome everybody to another lecture in the lecture series Explainable Machine Learning, and today we will talk about global model-agnostic methods, and we will specifically talk about feature importance, how you can compute feature importance, what advantages and disadvantages, and I will give you a whole palette of methods, what you can do and what actually importance means. And so let's get started. And again, I want to first talk about a simple example. In this case, an example where we perform instance segmentation, just as a reminder, so we are on the same page with the notation and that you actually know where we start. So what you can see here is an example of instance segmentation. You have an input image, you have an output instance segmentation. So each instance has a specific ID in this image. And here you can see a neural network with these blocks. These blocks illustrate the outcome after each layer or after each set of layers. And F is the classifier, this neural network. X is the input data. W are the parameters of the neural network, and Y is the estimated output. And we already talked a bit how you can reveal insights into a decision process, and one categorization is specificity. And today we will talk about one specific category, and as a reminder, we have two categories. The first one, illustrated on the top, is that you want to understand how the model relates the input to the output. So in this case, the model can be model agnostic, it can be black box, it can be, that means it's non-transparent, you don't need access to it, or you don't need access to the components. The only thing what you need for this is that you can input some data sample and you get an output, and this can be repeated as often as you need it. So you just have a look at the mapping. So when you change the input a little bit, what happens to the output? This is exactly what is analyzed here. The second one is different. This is a model-specific approach. Here you want to understand how specific parts of a network are responsible for a specific decision, a specific behavior. So here you find interpretation through methods that were tailored to specific models, for example, convolutional neural networks, or you want to look at weights in a linear model. And the basic difference is, so here you need access to the model, and here you can just ignore the whole architecture, the whole, how the model looks like. That's why it's model specific, and this is called model agnostic, and these approaches are mostly applied post hoc, so when the model is already learned. And today's lecture we will talk about this. Of course, it's in the title, and we will distinguish between another, or we will categorize it even further, and we will categorize it by locality. So here again you have two categories, and the first one is when you explain an individual output, and that means you have a look at specific decision and only one specific instance, and this will give you insights about the characteristic of exactly this specific instance. In the most cases, you want to have a look at an instance with some specific characteristic, or because you're especially interested in the specific instance. And the second one is when you want to explain the whole model behavior. That means for all data samples, for the whole data set. And this can be done, for example, by calculating a prototype, and which is maybe synthetic, typical example, which will lead to a maximum score. So here, this is a max score. As an output, this is what you want to reach. And this helps to understand when your model performs especially good, and so you can derive also insight when the model would fail. Yeah, and today we will have a look at this one. So we will have a look at global model-agnostic methods, and in the next lecture we will have a look at local model-agnostic methods. Of course, some of the methods I present today include that you have a look at local model-agnostic methods, and then you summarize the results from all of them to get some global insights. Okay, so as already mentioned in the last lecture, there are two major active research directions to get insights into a decision process of a machine learning model. And for today, I adapted this illustration a little bit. But again, these two major active research directions are visualization, and the other one is attribution. And for the first one, you have a look at the question, what does a model look for? And here we select representative samples from the data set, or we generate, for instance, examples which lead to high activations. In the last lecture, we also talked about approaches like visualization of components like model weights or some filters, but today we only look at model-agnostic approaches. This is why this is not not mentioned anymore. But also, of course, it belongs to this visualization procedure, to the category. For the second one, the second category or the second research direction, which is quite active at the moment, is attribution. And so here you look at the questions, which part of an example or an instance or a whole data set is responsible for the model behaving in a particular way. And here you highlight examples or parts of them. A typical example is this heat map, where one part is highlighted. So you see one hotspot here, and normally the image, when you work with images, this is overlaid, so you can see immediately where an important part in an image is. So this is where we, or this will be the topic of the next lecture. And today's lecture is also about feature attribution, but we will look at global methods and not specific images. And again, I already mentioned this slide in the last lecture, but for this lecture I made the definition a bit more general. Okay, and why I actually made this a bit more general, you will see in the next slides, because I will give you a little bit more an overview what actually attribution means and what different types of attribution there are, and there are quite a lot. Specifically 3, but when you look at the specific types, you will see there are a lot of different methods for attribution. Yeah, and I wanted to mention 3 general groups of attributions, and they all tell you how much an output is influenced negatively or positively based on changes in the input. And what you see here is a model. In this case a neural network, but it can be anything else that might be non-transparent. That means it's a black box model, that's why I illustrated in black. And the data instances you can see here with several feature dimensions and some output like a regression output or a class. And these data instances here exactly they're illustrated like boxes, and one box is one data instance, and the number in these boxes represent the single features. As already mentioned, there are different types of attribution, and the first one I want to present here is feature attribution. Feature attribution, for example, looks at specific features like a specific type of measurement. And very often this is referred to as feature importance. That means it's called feature importance in case you assume that the change in the output when changing the input is related to the importance of the feature. Exactly, then it's called feature importance. This can be done for a single instance or for the whole data set, and this is also illustrated here. So you have different instances, and here highlighted as one feature dimension, and you want to analyze the importance of this specific feature dimension. A related term is feature selection. Feature selection and feature importance analysis sometimes share the same technique, but feature selection is mostly applied before or during the model training to select the most contributing feature to the final prediction, while feature importance measures are used during or after the training to interpret and explain the learned model. That means it's mostly applied during or post hoc. So feature selection can be, for example, done manually, but the calculation of the feature importance involves very often a few computations. So feature selection very often is used in a remote sensing context. For example, when you think about what is important to predict a specific outcome, a specific parameters, and you select specific wavelengths of the sensor beforehand, so you can specifically choose an appropriate sensor, or you, when you already measured, for example, with a hyperspectral sensor, which is characterized by several hundreds of wavelengths which were measured, here you select specific wavelengths for your further analysis. So this is mostly done manually, and there are already a lot of insights, a lot of expert knowledge. But feature importance, and also what I'm talking here, is where we use methods and some computations to, or which tells us which features are important. So besides feature attribution, there's also pixel attribution. This is also called sometimes saliency mapping or heat mapping, which is a quite famous term. And it's a special case of feature attribution. So here important pixels in images are identified mostly for one specific instance. That means one specific image. So here, illustrated similarly to the last slide, is one instance, and you want to have a look at specific part and analyze if a specific part in an image is important for the output or not. And based on such analysis, you can derive such a heat map I showed you. But we will talk about it in more detail in the next lecture. And then there's instance attribution or data sample attribution, where the effect of specific instances of specific samples is analyzed. And the connected question is very often, how beneficial or how influential was the training sample for my model learning process? Of course, this is super interesting as soon as you can only collect a specific amount of samples, or if your computing resources is restricted, so you can only learn a model based on a few samples. So what you could, for example, do is you learn and or you very quickly you learn a model, and then you analyze which part of the instances were important for the prediction, and then you can take the fine-tuning step or the final procedure, which might take a lot of computation time. Here you only train the model with specific instances. Or for example, you could have a look at if specific instances or specific type of instances are missing. For example, when you know you have already instance would help you a lot, and you could, based on these insights, you could select further instances who could help you to improve your model further. So let's have a look at the advantages of model-agnostic procedures. First of all, you might think, why would it be good to ignore the model or treat it as a non-transparent, as a black box? But there are some advantages, and they can be actually summarized in the model flexibility, explanation flexibility, and representation flexibility. Model flexibility is a huge advantage because for a lot of real-world applications, you train for a high accuracy. So it's necessary. You want to solve your task, and of course you want to reach a good performance and a high accuracy. And this is irrespective of how complex or uninterpretable the underlying mechanism may be. And the perfect example for this are deep learning models. They are very often chosen because they are just good. They are good in solving the task, and they reach a high accuracy. So now, when you treat a model as a black box, that can be an advantage because the separation of the interpretation and the actual solving of the task makes it easier to learn an accurate model and still get insights into the decision process. Otherwise, you would need to choose the model based on what you want to interpret. So you have this separated, and you can get high accuracy, but also have the possibility to interpret the model and the result. Then there's explanation flexibility. So interpretable models are mostly restrictive to specific interpretations, and therefore also the explanation ability. And for example, you can extract rules, or you can extract prototypes, but generally the model cannot provide everything. So you need to decide on something. So you're restricted, and imagine you have a whole bunch of different users, and they have different preferences. So that might be difficult to choose what kind of interpretation you actually want to provide. And so if you want a specific type of interpretation, you're very restricted. And now when you separate the model learning and you want to solve your task, you choose a specific model and you separate it from the interpretation process, you are more flexible in what you can interpret and explain afterwards. So there are methods to extract prototypes, there are methods to extract rules, there are methods to extract a heat map, something like this. And you still have the same model, which hopefully performs really well on your task. And then there's representation flexibility. So when you use an interpretable model, you're restricted to the representation you have learned in the model. So for example, when you can visualize the internal representation, it might be still too challenging and too hard for the interpretation. And with model-agnostic approaches, you have the possibility to use a different representation than the one used by the underlying model. For example, you can learn a proxy model or proxy representation that is easier to interpret. I would tell one specific example in the next lecture when we talk about heat mapping, and there's a procedure called LIME, and here we work with a surrogate model, so we have a different representation which we use for the interpretation, and then the actual model used for solving the classification task. And what results from this is that you have, for example, a lower cost to switch. Since you have two separate parts, one is the interpretation and explanation parts, and the other one is the actual task solving part, you can, for example, switch the model and still have the same kind of interpretation afterwards, or you have different models, or you have the same the same model and you can switch the interpretation tool. So that's super easy, and you have the possibility of model comparison. So even if you have different kind of machine learning models, you can, if you treat them as or if you have a model-agnostic approach, you can apply model-agnostic approaches to get the same interpretation or the same kind of interpretation, irrespective of the kind of model. What is actually feature importance? Feature importance refers to techniques that calculate the score for input features for a given model, and the score simply represents the effect or the influence of each feature onto the model. And a higher score means the specific feature has a higher influence or a higher effect on the model output. And this is actually illustrated here. So what you have is you have some input, some samples with feature dimensions, and you have an output, and this output can be a classification output or a regression output. And illustrated here is the classification or regression model. The model is F, and the parameters of the model are W, and phi are the data samples, the input data. So let's get a little bit more specific. I was talking about effect. An effect is given by a specific score, which enables comparison. And it's your decision how you define importance and how you want to calculate the score. And one possibility is the change in the loss function value. Another possibility is a change in the prediction. And the difference becomes apparent for classification. For example, you can have quite a change in the loss function value, but no change in the prediction. And prediction means for classification tasks, class 1 or class 2, class 3, and so on. So in the end, you need to decide how or what you want and what is good for your interpretation and the computation of the feature importance. There are different types to manipulate the input. One method is permutation based. That means you randomly shuffle the input features. Another possibility is variance based. Here you add some noise on the input and you see how the output changes. And another possibility is occlusion based. What you do here is you occlude the feature. What that means, you replace it by a fixed value, for example 0 or 1, whatever comes most close or what is mostly related to covering up the input feature. Let's have a look at the specific procedure to calculate the feature importance, and this procedure is called partial dependence plots. The goal of partial dependence plots is to calculate the feature importance by calculating the marginal effect of the feature on the output. And what the marginal effect is, I will explain in a few seconds with an example, but let me first explain what you can see here. So what is illustrated here are the input features. So this is actually one sample with the index n, and you have illustrated 3 different features. So this is the output, this is the machine learning model, and L is the loss function. The input to the loss function is the actual prediction and the reference Y, sorry. And so what partial dependence plots reveal are insights into the relationship between input and output. For example, the complexity of the relationship. And complexity of the relationship means if the relationship between input and output is linear or quadratic or even more complex. And it comes with a visualization. That's why it's called partial dependence plots. And this visualization illustrates how the output varies when input features are manipulated. To see what a marginal effect is, let's have a look what a marginal distribution is. And imagine you want to order food after the lecture, after you listen to this here, but you only want to order food for the whole group. So I assume you're a whole group sitting in front of the monitor or in front of your smartphone watching this, and you want to order food after this. And that means the type of food is important, but not the single student, because you do not want to order for everybody. You only want to order food as a group. And what you do is you indicate your preference for pizza, burritos, and sushi from 0 to 10. So 0 is not good, 10 is super good. You want to order it. And so this is illustrated in this table here. So let's assume you have a group of 4 students and you have the choice of pizza, burrito, and sushi. And then we can compute the marginal distribution of pizza, burritos, and sushi, because this is what you want. And based on this, you make the decision what you actually what you want to order. And so that means the overall preference should be independent of the single students. And what you do is nothing else than summing up. And when you sum for pizza, it's 14, for burrito is 6, for sushi is 20. So obviously you like pizza and sushi, not so much burritos when you look at the whole group. So the marginal effect in our context with the feature importance is the contribution of a feature when other effects are marginalized out. So, so you want to get rid of something, and you want to what you interested in is the single features, and here you want to have the importance. Let's have a look at the data matrix. So the data matrix is just a collection of all data samples of the data instance you feed in. And I denote it with phi, and here you have given the number of samples, the index is n, and the overall number of samples is capital N. And then you have the feature dimension in this direction. And the index of the feature is d, and the overall number of all feature dimensions is d. Let's have a look at the procedure. And again, we have a look at the data matrix, but now we manipulate it. Remember, you compute the feature importance by manipulating the input, and then you see what happens to the output. So what you do is, first of all, for the partial dependence plot, you choose a feature of interest and you design artificial data samples. And these artificial data samples are collected in a data matrix phi prime. And in our case, the feature of interest is the one with the dimension d, here, this one. And what you do is you take, you select one feature in this dimension, let's say from sample m, and all the other samples get the same feature in dimension d. And all the other dimensions are fixed, and so all the values except in this dimensions are fixed, but the dimension d is replaced by specific typical value. And the typical value is just by selecting randomly from this dimension a specific feature. What you do then is you marginalize over the values of all other input features. That means you compute the output for all artificial data samples and average them. So this is illustrated in this equation here. So these are your artificial data samples, phi and prime. This is your function, your classifier, your regression from the machine learning model, whatever you want to output. And yeah, n is the number of all samples. And then you compute what is the output now with this artificial data samples. That means with the changed feature. And you repeat this for all m-1 values of this feature in dimension d of interest, and you visualize the dependence plot. And so let's have a look in how this looks like. So you have one dimension where you have all the typical samples, typical feature values of the samples here. And then you have this dimension, and this is the output value. And what you can see is how does it change? How does the output changes when you change the input values? And based on the shape of this plot, you can tell something. You can tell about the importance of the feature and what the relationship between the input and the output is. For example, if you have a plot like this, it means you have a linear relationship, because when you change the input, the output changes in a similar way. And also because it looks like this here and not like this here, it means it has a high importance. And yeah, speaking of no importance and looking like this, when you have a plot like this, it means when you change the value of the feature, nothing in the output will change. So it means it has no importance. But also you cannot say something about the relationship because this feature will not tell you anything about it. And this is something how it very likely looks when you perform it. So very often it looks like this. It means you have a non-linear relationship between the input and the output, and it has a medium importance. Medium means just in comparison to this first one. So in the end, it's also your decision when you define or how you define when a feature has a high importance, a medium importance, and no importance is mostly quite easy when nothing changed. Okay, so what are the advantages and disadvantages of partial dependence plots? So first of all, it's intuitive and easy to compute. Then it can be performed also for single instances. So here you get an impression of the whole data set, and so all samples are included. If you do it for individual samples, it's called individual conditional expectation, ICE. So what you do is you do not sum over the whole data set, but you change one feature dimension by typical samples, but you do not sum over the whole data set. And then partial dependence plot can also be calculated for more than one feature. That means these plots here get more dimensions. But of course, then the complexity of the plot increases. It assumes that the features are independent. This is a crucial thing. So it will destroy your interpretation, and it will destroy the plot, and it's misleading when features are correlated. Or also not only when it's correlated, but also when features interact with each other. And then for each value of a feature of interest, there's a whole path over the data set. So it means you need to calculate a lot, but in the best case, this calculation, it's not so computational intense. Besides partial dependence plot, also permutation feature importance is a simple way to compute the feature importance. And here, the goal is to calculate the feature importance by calculating the increase in model's predicting error after permuting the features. What permutation means, I will tell you in a few seconds. But overall, a feature is important if shuffling at values increases the model error, because in this case the model relied on this feature and it's considered as the feature as important for the prediction. And the feature is unimportant if shuffling its values leaves the model error unchanged, because in this case it's not necessary and not it's just ignored by the model for the prediction. And this procedure is sometimes called shuffle-based feature importance method. When I talked a little bit more about what permutation means, the name gets more clear. And this is illustrated here. What you can see is you have input features 3 dimensions. This is the machine learning model, F is the model, you have the loss function, and you have here the output. So let's dive a little bit more into the procedure. First of all, what you need is you compute the original prediction error. So this is what you need for this is your original data matrix. You have the feature dimensions, you have the samples. You have, one row is one sample. These are the single dimensions of the features. And what you then do is you manipulate the input. And you do this by permuting one feature phi dn and design a new matrix phi prime. And so what you do is normally the original value was phi dn, but what you do is you permute the phi dn. So then it's replaced by another feature value from this dimension. In this case, it's denoted with phi dm. So what this permutation actually means, because there are different possibilities. What you can do is you loop over all samples with several repetitions of random swaps of feature values. So what you do is here you identify one dimension, the feature you are interested in, and then you identify one specific sample, and then you swap the feature value of the sample with another feature from another sample. So you swap randomly, and you can even think about a more complete procedure, not only randomly a little bit, but a complete procedure by choosing a sample and then swap the feature of the sample with the same feature of all other samples. So complete swapping, not you can also do it randomly, it's much faster then. An alternative, also not so computationally intense method is when you split the training data set into 2 halves and swap the feature values. So there are different, the basic principle is just swapping features in the same dimension, and how you do it, there are actually a lot of possibilities. So the remaining procedure after the permutation is then you compute the prediction error with a permuted feature matrix, and then you repeat and average it. So you do this random swaps and then you recompute it, so how it actually changes, and you do this with a lot of samples. Of course, you see, if you do it in a complete way, it means a lot of computation. So normally this is there's some randomization effect in it, so that it's not that is approximated. And then you can compute the permutation feature importance in mainly 2 ways. For example, you can take the quotient or the difference. It depends on what you think is better. In the end, what you do is you have a new value after you permuted the input feature and afterward and before. So with permutation and without, and you compare it. The advantages are it's easy to handle and easy to understand, but the usage of the error, when you use the error ratio, it allows for comparison across different tasks, because if you have the ratio, it will give you some a more comparable score when you so that you can compare it across different tasks. And there's no retraining required since the feature is permuted and not deleted. This is one crucial thing which is necessary, or which are both which are most feature importance methods are based on. So what you do not want to do is you want to take out a feature, because when you take it out, you need to retrain the whole machine learning model. Then it's not model agnostic anymore, and you need to change the model. And this is not what you want. So you need to find somehow a procedure to manipulate the input without the need to retrain your model. The disadvantage is, first of all, the permutation feature importance is linked to the error or the loss function of the model. This is not inherently bad, but in some cases this is not what you need. In some cases you might prefer to know how much the model outputs varies for a feature without considering what it means for performance. Then also you need access to target variables, because when you deal with the loss function you need to compute it somehow. So you need your reference values, that means the target variables. And then the permutation feature importance depends on shuffling the feature, which adds randomness to the measurement. And when the permutation is repeated, the results might vary greatly. And repeating the permutation and averaging the importance measures over repetitions stabilizes the measure but increases the computation. So you somehow need to find a compromise between an efficient computation and the variance of the computation need to be found. There's not a good rule of thumb, but it depends on the variability of the data set, for example. So you need to decide and how much you actually compute from the whole possibilities of permutations. Then a problem is that the permutation can lead to unrealistic features, and features are assumed to be independent. This is a little bit related because the permutation leads to unrealistic features in case features are correlated or somehow not independent. Because if they would be independent and you use reasonable feature values, there would not be unrealistic data samples. So this is not specific for this method. This is a problem for all feature importance methods. Or not really a problem, but it's an assumption you need to fulfill. And let me go a little bit more into detail in the disadvantage of feature correlation and feature dependence, feature interaction specifically. So feature correlation means that some feature phi1 or some features phi1 and phi2 are dependent to each other regardless of the target prediction y. In other words, we can say if we increase feature phi1, then also feature phi2 will increase or decrease. So they are connected, they are correlated. And when two features are correlated and one of the feature is permuted, the model will still have access to the other one through its correlated feature. The result is actually illustrated here. The results is that there will be a lower importance value for both features because the model error might not increase. Another problem is feature interaction. It's not a problem in general, but it's a problem when you compute feature importance. And feature interaction is a little bit different to feature correlation. Here you have independent features, but they're simultaneously important for model prediction. So a feature interaction describes a situation in which the effect of one feature on an outcome depends on the state of the second feature. And it is a non-additive effect between multiple features on an outcome. And a very naive example is if you have two features, and one feature would be the absolute value of the measurement, and the other one would tell you if the measurement is positive or negative. So one feature alone does not make sense, but together they will actually contribute, hopefully, to the output. So the features alone are misleading. And the importance of the interaction between two features is included in the importance measures, importance calculation of both features. That means that the feature importance do not add up to the total drop in performance, but the sum is larger. So if you change one, it drops a lot. If you change the other one, it might drop a lot, but it should only drop together a lot. So that's that's actually, so it's actually a problem when you only look at one single feature and not they are not together. Of course, you have the possibility to look at them together. Okay, so there is also a relation to decision tree feature importance. So decision tree feature importance is something which is used on a regular basis because also random forests are a quite powerful tool. And for classification and regression. And so first of all, decision tree feature importance is computed based on a splitting criterion. That means samples will decide for some decision paths in this decision tree, no matter if the sample is out of distribution or not. And so it will give you any result. And this can lead to high feature importance values for out of distribution training, training data distribution test samples. So test samples which are different to the training data distribution. That's a problem because it's totally misleading. And then decision trees are biased towards the favored usage of high cardinality features. So high cardinality is means the number of or the number of values the features can take. So binary features have a low cardinality, and continuous features have a high cardinality. And decision tree tend to use more these high cardinality features for the decision and the splitting. And permutation-based feature importances do not exhibit such a bias, and additionally the permutation feature importance is model agnostic. The decision tree feature importance is not model agnostic, and so this permutation-based feature importance can be used to analyze any model class, not just tree-based models. So just to give you an overview about the differences, but nevertheless, decision tree feature importance is mostly a good tool in case you are anyway using decision trees or random forests, and this is what you are interested in. And another possibility to compute feature importance is the variance-based feature importance. This is a very, very easy method, and here the goal is to calculate the feature importance by calculating the increase in the model's predicting error after adding noise to the feature. And this is illustrated again here. So similar to the to other feature importance calculation methods, you have input features, you decide on one feature dimension, and then you manipulate one feature dimension, in this case the first one, and here you add noise and you have a look on the output, for example by looking at the loss function value and how it changes. And to briefly mention the advantages and disadvantages is, first of all, it prevents unlikely and unrealistic data samples, even if you have correlated features. But again, unrealistic samples are anyway a bad sign, since this happens when features are correlated, and constellations get unrealistic when you break the correlation. And then a disadvantage is that you might not reflect the marginal distribution well enough. So when you add noise, sometimes it might be reasonable, but for example, if you have if your feature values have a very complex distribution, adding noise might not really reflect how this feature would behave. So you get a wrong impression, a misleading impression, and how important a feature dimension is. So far, we talked only about features, but also the data sample. The data samples highly influence the model during training. So it would be good to analyze if typical data points do exactly what you want, and not so well represented data points don't have weaknesses which you would need to fix. So the problem is now, imagine I give you 1 million data samples, and so you cannot check them all, and so instead you need to select a few to get an impression of your data set and an impression how your model behaves given the data, and how the model behaves given specific data samples. And a good choice are prototypes, which are representative samples. And let's assume you have a data set, and here you have given some data samples, and can be a very high dimension space, images, whatever you're interested in, or what you have given. And for example, these two blue dots, data samples, can be seen as prototypes. So prototypes represent the data set, so you would say, okay, if they somehow represent and cover up how the data is distributed, but what about these two areas? They are a little bit, or these clusters are a bit isolated, they are not so represented well by the prototypes, but they should not be ignored. So somehow they should also be represented. And so obviously prototypes are not enough, and we need more to describe our data. And for this, criticisms have been considered in the literature. And to give you a definition, so prototypes are highly representative samples of the whole data set. And criticisms are diverse samples that are not well represented by the prototypes, but they still, are proxies together, the prototypes and criticisms together serve as a proxy data set to understand the decisions of the model. So instead of using the whole data set and randomly choose what you analyze, instead of randomly choose the data samples to analyze the model behavior, you can use prototypes and criticisms as representative samples. Okay, the question is now how to select prototypes and criticism. First of all, prototypes and criticism need to be data samples. This makes sense because otherwise they might not be realistic. For example, if you think of images, even if you have a close by area around this data point, this image, it can get unrealistic, blurry, or whatever. So it's a good idea to stick to data samples, to real data samples. Then the distribution of the prototypes should be close to the data distribution, because you want to represent the majority of the data, or the majorities in the data. That means dense clusters. But then, as you have seen in the example I showed, criticisms should be also located, or they so criticisms should be located in areas where the distribution of prototypes and the data distribution are most different. That means with criticism, minorities in the data are covered. So it means we do not speak about outliers. We speak about dense areas which are a little bit isolated, so they're minorities, and so they should be represented. They're still representative of the data set, but they are not so representative for the whole data set that the prototypes might find them. So we have majorities and we have minorities, and both should be represented, and both should represent the whole data set. And what we need to find them both is, first of all, the maximum mean discrepancy, MMD, and we need a witness function. And I will show you in the next few slides how you can use them. So let's dive a little bit more into the procedure. First of all, you choose the number of prototypes in criticism. A good procedure is to start with a low value, not too many. You can still, if you see they're not enough, you can still increase it. Then you select the prototypes with the MMD measure in a greedy manner. Greedy means you start with an empty set and then you increase the number and see how the set grows and how the current selection or the next selection of a prototype will influence the previous selection of the prototypes. And also the criticisms are selected in a greedy manner, but using a witness function. And for the notation, so the prototypes are denoted with R and the criticisms are denoted with C. And since we don't want to work with the data alone, but with distribution, we can use a kernel function. And the kernel function illustrated here, K, kernel function K, is nothing else than a function centered on a data sample that allows to calculate a proximity to all other data samples in the surrounding area. A special case is the Gaussian radial basis function kernel. This is when you have this together here. This is very often used. And what is actually seen here, so this is the squared Euclidean distance. So you have a data sample phi n, and you have a prototype, and you have a squared Euclidean distance, and you have gamma here, which is a scaling parameter. And if you choose this here as a scaling parameter, you have a Gaussian radial basis function kernel. The value of the kernel decreases with the distance between 2 points and ranges between 0 and 1. 0 is when the 2 points are infinitely far away from each other, and 1 is when 2 points are equal. And when you select prototypes and you use kernels, we can create a density distribution of the prototypes, and so we can, for example, evaluate whether the prototype distributions differs from the data distribution. So I have the possibility, when you compare these two distributions, how good the prototype distribution approximates the data distribution. So let's have a look in how we can select the prototypes. So the whole procedure, as I said, is a greedy procedure. That means we start with an empty set and add further prototypes based on the MMD criteria. What we do in detail is that we take a sample from the data set, add it to the set of prototypes, and then compute the squared MMD distance. So we actually have a potential prototype, add it, and see what happens. So what we can see in this equation here, this is the MMD criteria. So capital P is the number of prototypes, capital N is the number of data samples, and what you can see is you have three parts and in this equation. So also k, as a reminder, is a kernel function. All these parts include a kernel function which computes, which compares these samples and compute proximities. So the first term computes the average proximity between all prototypes. So this is the kernel function, and you have all prototypes included here. So this is, in the end, you have proximities between all the prototypes. The second term is 2 times the average proximity between the prototypes and all other data samples. Why it's 2 times, I will tell you in a few seconds. And the third part is the average proximity between all data samples. So here in the kernel function, you have all data samples included. And if the middle term adds up to the first term plus the third term, then the prototypes explain the data perfectly. That's why it's 2 times, because then it's, it's when the middle term actually exactly add up to the first and the second one. And you know when this would be the case, it's exactly when all data samples are prototypes. It makes totally sense, but this is not what you want. What you want is you want to select your prototypes to come as close, but not to have them all, because then you didn't do anything, just computations. Okay, so what in the end what you want to have is you select the prototype and not a random one, but the one with a minimum MMD measure. And so what you do is you test every data sample to be a prototype, compute this, and you select a prototype with a minimum MMD. Then what is left is a selection of criticism, and for this we define a witness function which tells us how much 2 density estimates differ at a particular point phi m. So what we have is we have 2 data sets. We have one set of prototypes and we have the data set. And for both we have density, since we are working with kernels. So for the 2 data sets, the witness function evaluates how good phi m fits to these densities. So what the witness function does is it has 2 parts, and then computes how good is phi m represented by the prototype data set and by the whole data set. Yeah, so these are exactly the 2 terms. To be a little bit more specific, so the first term is the average proximity between all data samples and the potential criticism. And the second term here is the average proximity between the prototypes and the potential criticism. So it will tell you a little bit of how much is already represented by the prototypes, but also if the potential criticism is more like an outlier, or if it still fits good to the overall data distribution. So let's see what happens in different scenarios. So what is important is there's a minus. So we have 2 terms, 1 term, second term, and you subtract the second one from the first one. First scenario, if the witness function is close to 0, then both terms have an equal, nearly an equal value, which means both densities are similar. So it means the prototypes represent the data distribution in a good way, and that specifically it's represented well at the point phi m. So we need to keep in mind that everything here is evaluated in the proximity of the point phi m. So if the witness function is negative, the first term is small and the second one is large. That means that the prototype distribution overestimates the data distribution. That means the prototypes were selected where the density is small. So you selected too many prototypes. And the third scenario is if the witness function is positive, the first term is large and the second one is low. That means that the prototype distribution underestimates the data distribution. So actually prototypes are missing. So somehow it happened, or it happened that the prototypes could not find specific areas. And so, yeah. And keep in mind, again, everything is evaluated at 0.5 m. So criticisms are now selected by choosing the samples with a high absolute value, exactly where both distributions diverge. So from the scenarios, this was exactly when either this was large and this was small, or this was, so the first term was small and the second one was large. Then you have a high absolute value. And very often there's also a regularization which is added so that the criticisms are diverse and not close to each other. So let's come back to our dataset example. So let's say we found two prototypes. We already agreed on this, that they're good representative of the dataset. So you have here high density area, here high density area. And you said, okay, we found two prototypes in these high density areas, and then two potential criticisms, here illustrated in yellow, can be exactly these, where the data set is underrepresented from the prototypes, but the data distribution is high. This might, for example, happen if you have a high density area, but it's actually a little bit isolated, a little bit an isolated cluster. In case prototypes would have been selected in areas where not so many data samples are, I mean, you might think about why not just selecting more prototypes. You can do it. A criticism would have been selected also in this area. And so you get an indicator that the data distribution is overestimated in the area. So the thing is, so the prototypes and the criticisms only, especially the criticism, only makes sense if you always look at them together. So that's an important thing, because the selection of the criticism depend on the previous selection of the prototypes. So how does it help now for the interpretability? First of all, it helps to understand the data better. And it provides data samples for analyzing the decision process. So what you do is you select your prototypes and your criticism, and then you can compute feature importance with these representative examples, because you cannot do it with 1 million samples. Or you can, what I tell the next lecture, you can perform heat mapping or something like this. And the good thing is that first of all, it identifies weaknesses. So when was the model wrong? And it identifies optimal data samples. So for this is prototypes. Prototypes are very often very typical samples which lead to an optimal, that means a very high score, a very good result. And it's interesting to know for which samples gives the model the highest scores. But the criticisms are especially interesting for edge cases. That means, and here this is exactly what I mean with it identifies weaknesses. So these minorities in the data, these these high density areas but isolated areas in the data set are edge cases, and so it might be really interesting to look at them, and prototypes might miss them. So let's talk a bit more about advantages and disadvantages. So User studies show that prototypes and criticisms are easy to identify. That's good. What has been done is, so when you have a million of images, and so you select prototypes and criticism, and you give them to users, these are normally the samples which are easy to identify even if they are not an expert in this area. So this is a good thing, so that it means these samples are representative of the data set. And these data samples help you to easily understand complex data, so that's useful. But a disadvantage is that the sets of prototypes and criticisms depend on the number of prototypes. So this is also what you might already identified. So it's worth to invest testing what is a good number of prototypes. And there are influential hyperparameters like the kernel width, and it also highly influence the result. So to sum up, what I showed you today were global model-agnostic methods, and they give you an impression about the general decision process of the model. Of course, I selected a few, but there are a lot more of them out there. But I hope you could identify the basic procedure, the basic idea behind it, and and also see the variety what is out there. And the good thing about model agnostic approaches is they have a high flexibility regarding the model, the interpreted entity, and the representation. This is what exactly I mentioned in the beginning. So they have a model flexibility, explanation flexibility, and representation flexibility. And the basic reason for this is that you have a separate interpretation explainability part and a model learning and task solving part. With this, I thank you very much for listening, and I hope to see you in the next lecture when we talk about local model agnostic methods. Thanks a lot.